Welcome to UTC AI Studio, AI-powered, creativity-fueled. This video brings together all 9 episodes of our Phase 1 AI Foundation series. If you're new to AI, this one continuous journey will take you from zero to fully understanding the core ideas behind modern artificial intelligence. Artificial intelligence. You hear that term everywhere these days, right? It's either this amazing thing that's going to save the world, or it's coming for all our jobs. But the truth? The reality of AI today actually a lot simpler, and honestly in some ways far more powerful than all that sci-fi hype. So let's cut through the noise and figure out what's really going on here. To get started, let's make this personal. Just think about it for a second. How many times have you actually interacted with AI today? I'm willing to bet that the answer is way higher than you think, because AI isn't some futuristic movie idea. It's already here. If you watched a movie recommended by Netflix or asked your phone about the weather, noticed autocorrect fixing your typos, or saw Google Photos grouping faces together, means you've already used AI. And if your inbox isn't drowning in junk mail, that's AI too. It's this powerful, often invisible engine that's already running our world. What is artificial intelligence? So that brings us to the big question, what is artificial intelligence exactly? To understand it, we need to look past the Hollywood idea of thinking and feeling robot, strip it all down, and AI is basically the science of building machines that can do things that normally need a human brain. Things like reasoning through a problem, learning from experience, and then acting on that knowledge to reach a goal. Now here's an important distinction. On one hand, you've got general AI, the Hollywood dream of a machine as smart and flexible as a person, but that's still just theory. It doesn't exist. Then there's narrow AI, and this is the real game changer. This is the AI we actually have all around us today. These are super specialized tools built to do one thing incredibly well. Think of Google Translate. It doesn't understand language like we do, but it's insanely good at spotting patterns and producing useful translations. Or take a search engine scanning the entire internet, or a chess computer beating the world's best player. That's narrow AI in action. How does artificial intelligence learn? So if these systems aren't thinking the way we do, how do they get so smart? Let's pop the hood and take a look at how AI actually learns. The answer is something called machine learning. Instead of a programmer writing out rules for every possible situation, we let the machine teach itself. We feed it mind-boggling amounts of data, and it learns to spot patterns and make decisions on its own. Here's a simple breakdown. First, you need data. Huge amounts of it. Imagine millions of cat pictures. Then algorithms go to work sifting through all that data to find patterns which makes a cat look like a cat. That's the training phase. The model keeps tweaking itself over and over, trying to get more accurate. Next, you show it a brand new picture it's never seen, and it makes a pretty good guess. With feedback, it keeps getting smarter. That's why your spam folder can catch junk emails you've never seen. The model has already learned what spam usually looks like. And the secret sauce behind all of this? Something called an artificial neural network. You can think of it like a computer system loosely based on how our brains are wired, processing information in complex layers. It's not perfect, but it's a powerful way of copying how humans learn. Types of AI. Now that we know how AI learns, let's look at the different kinds of this process creates. Here's a simple framework, 4 stages of AI. First up, reactive machines. Think of the chess computer Deep Blue. It only reacts to the current board. No memory of past moves. Next is limited memory AI. This type can use recent data to make better decisions. A self-driving car is the perfect example. It remembers the last few moments of traffic to navigate safely. Then we have theory of mind and self-aware AI. These are still pure science fiction, for now at least. And that leads to a crucial takeaway. From Netflix recommendations to cutting-edge medical tools, almost every piece of AI we use today is limited memory AI. It's incredibly powerful, yes, but it is not conscious. If you're enjoying this so far, hit like and subscribe to stay updated as we explore AI step by step. Real-world impact. Now that we've got the basics down, let's look at how limited memory AI is already transforming our world. In healthcare, AI acts like an expert assistant. It can scan medical images and spot tiny details a human eye might miss, helping doctors catch diseases earlier. In finance, AI works around the clock. It's the system that flags suspicious charges on your credit card in seconds, and it analyzes complex market data faster than any team of humans ever could. In science, the scale is astronomical, literally. Instead of scientists spending years manually counting galaxies in telescope photos, an AI can be trained to do it in a fraction of the time. AI is speeding up discovery in ways that are hard to even comprehend. Promise versus challenges. All this rapid progress makes many experts believe we are stepping into a brand new era. One is filled with incredible promises, but also serious challenges we must face head-on. As AI expert Professor Mike Woolridge puts it, something big shifted around 2020. It was a genuine watershed moment, kind of like when the World Wide Web first appeared. And now, major changes are happening in months, not years. The promise of this new era is immense. Imagine a world where machines take on dangerous jobs, where human mistakes in critical tasks are almost eliminated, and where scientific breakthroughs happen at lightning speed. Or look at repetitive work like call centers. Many already use AI chatbots that handle thousands of customer queries at once. The ultimate goal? To take over the boring and dangerous jobs and free us to focus on what we do best: creativity, strategy, and connecting with each other. But, and this is a big but, this power also forces us to face massive challenges. If you train an AI on bad data, you'll get bad results. What happens to people whose jobs get automated away? And how can we trust black box systems when we don't even fully understand how they make decisions? These aren't future problems. These are questions we must answer right now, which leaves us with one huge question. Is AI truly going to free us to be more creative, more strategic, more human? Or will the challenges outweigh the promise? The truth is, nobody knows yet. The story is being written right now, and every one of us has a role to play. Now that you understand what AI actually is, let's break it down further, starting with the difference between AI, machine learning, and deep learning. So, have you heard words like artificial intelligence, machine learning, deep learning, and generative AI? They're all over the news. They're in every business meeting. And here's the thing, people often throw them around like they all mean the same thing, but they don't. So, what's the real story? Are these just different buzzwords, or do they actually mean something different? It can be confusing, and you're not wrong to feel that way. Well, that's exactly what we're here to clear up. My goal is to give you a super simple, easy to remember model for how these powerful ideas fit together. And hey, this isn't just for the tech geeks in Silicon Valley anymore. Mark Cuban really nailed it when he said, if you're not using AI to move faster or make smarter decisions, you're behind. The world is moving fast, and having a basic handle on this is essential for everyone. This is the granddaddy of them all, the original dream that kicked this whole revolution off decades ago. What is AI really? Well, you can think of it as the huge overarching goal of making machines smart. It's the field of building computers to do things that once needed human brains. It's the whole universe of trying to get machines to think, reason, and act like us. Now, human intelligence is a pretty massive term, right? So what does that actually look like for a machine? Well, it really boils down to a few key things. The ability to learn from experience, to figure things out, to reason through problems, and crucially to perceive the world. To see things with computer vision and to understand what we're saying through something called natural language processing, or NLP. And you might think AI is this brand new thing, but no way. This dream has been around for a long time. Most people point to a project at Dartmouth way back in 1956 as the official start. From there, the military got interested, which led to things called expert systems in the 80s and even early versions of early digital assistants, way before Siri. The point is, AI is built on decades of work. Okay, so if AI is the big destination, let's say landing on Moon, how do we actually build a rocket to get there? Well, that brings us to our next stop, machine learning. And here's the most important thing to get. ML isn't a separate competing idea. It's one of the most powerful tools we have for actually building AI. Machine learning is a specific part of AI, and its central idea is a total game changer. See, instead of a programmer trying to write a rule for every single possible thing that could happen, they just feed the machine large amounts of data and let it figure out the patterns and rules for itself. It literally learns from experience just like we do. And this really shows you how different the thinking is. The old way was programming everything explicitly, if this then that. It was super rigid and would break the second it saw something unexpected. But with machine learning, you don't write rules, you train a model. You just show it large amounts of data. And the crazy part is, the more data it sees, the smarter and more adaptable it becomes. And guess what? You're already living in a world run by machine learning, probably without even thinking about it. That perfect song Spotify cues up next. That's ML. The movie Netflix knows you're going to love. ML again. When your bank sends you a text about a weird charge, that's machine learning protecting you. If you're finding this breakdown helpful, hit that like button so more people can discover it. And make sure to subscribe to UTC AI Studio. Alright, so now we're going to zoom in even further. Let's say we've got our rocket engine with machine learning, but what if we want serious rocket fuel? That's where deep learning comes in. Inside this world of machine learning, there's a technique that's been responsible for some of the biggest breakthroughs we've seen recently. It's called deep learning, and it's basically inspired by the wiring of our own brains. So deep learning is a super specialized type of machine learning, and its secret weapon is something called an artificial neural network, which is just a fancy way of saying it's a computer system designed to work kind of like the network of neurons in your head. And these networks are just incredible at finding super complex patterns in huge messy amounts of data. So why do they call it deep? Well, it's because these neural networks aren't simple. They have many layers. Data comes in at the top, then it passes through all these hidden layers. Each layer it goes through, it learns to recognize something more complex. The first layer might see simple lines, the next layer combines them into shapes, the next layer recognizes objects, like eyes or a wheel. Finally, the output layer makes a really smart decision about the whole thing, until finally it says, "That's a cat." And the things this makes possible are just wow. Deep learning is what let Google's AlphaGo beat the world's best player at Go, a game that's way more complex than chess. It's the engine that lets your phone understand what you're saying. It's how self-driving cars can see, understand, and navigate roads. And it's even being used in medicine to spot tumors on scans, at times better than human doctors. And building on deep learning, we now have the next frontier, generative AI, which everyone is talking about these days. Now, don't think of this as something totally new. Think of it as the newest and most exciting branch growing out of this tree we've just described. It's built on everything that came before it. So, what's the big deal with generative AI? Well, while all the earlier models were amazing at analyzing or categorizing things, generative AI is all about creating things. Using these massive models, like the large language models powering today's AI tools, it can create everything from text to pictures to music. You name it. Now, some people say, oh, it's just mashing up things it has seen before. But here's a great way to think about it. All music is just a recombination of the same 12 notes. But we don't say new songs don't exist, right? Generative AI is kind of like that. It's using what it knows to combine ideas in genuinely new and creative ways. The big picture. Okay, we've covered a ton of ground here, from the big dream of AI all the way down to the details of deep learning. So now let's pull the camera back and put it all together. When you see it like this, the relationship is actually pretty simple. The best way to picture it is with Russian nesting dolls. Artificial intelligence is the biggest doll, the whole concept. Open it up and inside you find machine learning, a specific way to build AI. Open that one and inside you find deep learning, an even more specific and powerful way to do machine learning. And emerging from within is generative AI, the newest branch built on top of everything that came before. Together, they're not rivals. They're all part of the same story of intelligence. Key takeaway. So, the number one takeaway here is that these aren't opposing teams. They're all on the same side. AI is a big dream. Machine learning is a practical strategy to get there. And deep learning is one of the most advanced tactics in that strategy. Each one is just a piece of the one before it. And why does knowing this matter? Well, it's not just trivia. Understanding this stuff is becoming an incredibly valuable skill. According to the management consultancy McKinsey, up to 30% of hours worked across the United States economy could be automated by 2030, with 12 million occupational transitions required by the same year. And as the World Economic Forum estimates, while over the next few years there might be 85 million job losses across the globe, new technologies could create as many as 97 million new jobs. In short, the skills the average worker possesses will change dramatically over the next 10 years. And that leaves us with one final big thought. These technologies, built one on top of the other, are already solving problems we never ever thought a computer could solve. So the real question now for all of us is, what's next? What are the biggest, most important challenges we should aim for this incredible new intelligence at? So we've gone from artificial intelligence as the big dream to machine learning as the strategy, to deep learning as the advanced tactic, and finally generative AI, the newest branch that's reshaping everything. Now here's my question for you. What do you think AI should be used for next? Let me know in the comments. To understand deep learning properly, we need to look at the building block that makes it possible, the neural network. Have you ever just stopped and wondered, how does a computer actually learn to see? It really feels like magic, right? Well, today you're going to see that magic turns into logic. To recognize your cat in a photo or translate a sentence or even drive a car. But deep down, it's all based on this incredibly cool idea that's actually inspired by our very own brains. So today, let's pull back that curtain. We're going to build a neural network right from scratch. And we'll start with a problem that's super easy for us, but for a machine, well, it's a whole different story. So we all know that this is a 3, no question. I mean, it's sloppy, it's low resolution, but our brains just get it instantly. You could show hundreds of different versions of a messy 3, and our brain knows it every single time. But for a computer, this is a huge challenge because a computer doesn't see a 3. It just sees, well, a grid of 784 pixels, each one with a different shade of gray. So the real question is, how do you teach it to find the idea of a 3 buried in all that messy data? The task goes from comically trivial to dauntingly difficult. What's a complete non-issue for us is a massive hurdle for a machine. And the key solution to this whole puzzle is something called a neural network. Alright, to really get how this whole thing works, we've got to start small. I mean really small. We need to zoom all the way in and look at the most basic building block of the entire system. Just one single artificial neuron. First thing first, when I say neuron, I don't want you to picture some complicated cell from your biology textbook. In our world, it's way simpler. A neuron is basically just a thing that holds a number. That's it. And specifically, it holds a number between 0 and 1. We call this activation. Think of it like a dimmer switch. 0 means the light is totally off and 1 means it's on at full blast. And anything in between is somewhere in between. Seriously, that's all a neuron is at its core. Alright, it holds number. Big deal, right? What does it actually do with that number? Well, you can think of a single neuron as a tiny little decision maker. And to really understand how it makes those decisions, let's use a fun everyday example. Let's say our little neuron needs to make a classic decision. Should we go surfing or not? So it looks at a few things. First, are the waves good? If yes, it gets a 1. Second, is it crowded? If yes, for the factor of empty lineup, that's a 0. And third, are there sharks? If no, that's a 1 for being shark-free. Now here's the key. Not all these factors are equally important, so we give them an importance which we call a weight. Good waves are a huge deal, so that gets a high weight, let's say 5. Being shark-free is also pretty important, so that's a 4. And crowd's less of a deal breaker, so that's a 2. We just multiply each factor by its weight and add it all up. Finally, we subtract something called a bias. We'll use 3. You can think of the bias as the neuron's natural laziness. It needs a good reason to get going. So what do we get? The final score is 6, and since 6 is definitely greater than 0, the neuron activates. The dimmer switch cranks all the way up to on. The decision is made, we're going surfing. Every single neuron in the network is just making a simple little decision, exactly like this one based on the weighted information it gets and its own little bias. Alright, so we get it. One neuron is one tiny decision maker. But obviously one of these little guys can't recognize a handwritten number on its own. The real magic, the real power happens when we start connecting thousands of them together and when we assemble them into a network. A typical neural network has this really clean layered setup. It all starts with the input layer. This is just where the raw information gets fed in. For us, that's the bright value for every single one of those 784 pixels. Then at the very end of the line, you've got the output layer. This is what spits out the final answer. But the really interesting stuff, the real magic happens in the middle, in what we call the hidden layers. This is where the network actually starts to figure stuff out and find patterns. So, let's get specific for our digit recognizing network. Here's the blueprint. The input layer, it's got 784 neurons, one for every pixel in the image. Then we've got those middle hidden layers. We're going to use 2 of them, each with 16 neurons. Now what are they actually doing in there? Honestly, for right now, that's kind of a black box. A bit of a mystery, we'll get to that. Finally, the output layer has 10 neurons. Why 10? Simple. One for each digit from 0 all the way to 9. And whichever one of those 10 neurons lights up the brightest, that's the network's final guess. Now let's tackle that mystery. What on earth is going on inside those hidden layers? This is where we figure out how these things actually think. So let's crack open that black box. The big idea. And it's actually beautiful in its simplicity. The network learns by building things up by step in a hierarchy. Each layer learns to spot more complex patterns, but it does it by using the simpler patterns that the layer before it already found. It's like building with Legos. Let's trace how it would recognize, say, the number 9. The first hidden layer, it's not looking for a 9, it's way too simple for that. It just learns to spot tiny basic things like little diagonal edges or small horizontal lines just by looking at the raw pixels. Then the second hidden layer looks at what the first layer found. It sees the pattern of activated edges, and it learns to combine them into bigger shapes. It's basically saying, hey, if I see a bunch of these little edged pieces arranged in a circle, that's a loop. Or if I see these other edges all in a row, that's a long straight line. And then finally, the output layer takes those components, the loops and the lines, and puts it all together. It learns that a pattern of an upper loop connected to a long vertical line, well, that's a 9. It's incredible. We've got this amazing structure that can theoretically see a digit by building up patterns. But how does it learn which connections are the right ones? How does it figure out that these edges make a loop, and that loop and line combo make a 9? Well, that's where the whole process of training comes in. The way a network learns is by tweaking thousands and thousands of tiny dials and knobs. And there are two types. The first are the weights. Think back to our surfing example. The weight was how important the waves were. Here it's the same idea. A weight controls how strong the connection is between two neurons. The second type are biases. You can think of a bias as basically setting that threshold we talked about. It makes a neuron either easier or harder to activate. So you've got all these weights and biases, thousands of little knobs that network can turn to tune itself and better. But how many knobs are we talking about? For our simple and digit recognizer, there are almost 13,000 of them. 13,000 individual dials and knobs that have to be tuned to just the right setting for this thing to actually work. I mean, trying to do that by hand, forget it. It would be completely impossible. So, how in the world does it tunes all 13,000 of those knobs correctly? Well, it does it through a very smart process called learning. It's a trial and error process. Basically, you show the network thousands and thousands of examples of handwritten digits. And for every single one, it makes a guess, gets feedback on how wrong it was, and then it makes a tiny little adjustment to those knobs to get just a little bit closer to the right answer next time. And that whole learning process happens in a constant 4-step loop. First step, then network gets an image and makes a guess. We call that the forward pass. Second step, it checks its guess against the real answer and calculates how wrong it was. That's the error. Now the third step, this is the really clever part. It works backwards through the whole network to figure out which of those 13,000 knobs were the biggest culprits for the mistake. This is a famous process called backpropagation. And finally, the fourth step, it tweaks those specific knobs just a little bit, hoping to do better next time. And this loop just repeats over and over and over again across thousands of examples until all 13,000 knobs are tuned perfectly. And the network slowly but surely learns how to see. Now, it's really important to remember that what we've just described here, it's kind of like the Model T of neural networks. It's the classic, the original, but it's just the beginning. This basic idea is the foundation for all kinds of specialized, way more powerful networks. You've got things called convolutional neural networks, which are absolute wizards when it comes to images. There are recurrent neural networks that are built to handle sequences like language or speech. And then you have transformers, which are the incredible engines behind those huge models like GPT that are changing everything. Just end on this one thought. We just saw how a pretty simple network can teach itself to understand an abstract idea like the number 9 just by learning to see patterns of patterns, starting with pixels, building up to edges, then loops and lines. Does it really make you wonder, doesn't it? If that's what a small network can do, what about the biggest ones? The ones with billions of neurons and trillions of connections. What kind of patterns? What kind of fundamental truths about our world are they learning to see right now? These neural networks power the AI models you use every day, especially the ones behind text, chatbots, and creativity tools. So next, let's explore the biggest breakthrough in modern AI. Have you ever just sat back and wondered how an AI can write a beautiful poem, or draft a perfect email, or even spit out lines of code that actually work? Well, the answer is a technology that is no joke reshaping our world. Large language models, or as you probably know them, LLMs. Let's spend the next few minutes breaking down exactly how these things tick. How do tools like ChatGPT, Gemini, and Claude go from a totally blank slate to having a conversation that feels almost human? You'd think the answer is insanely complicated, and in some ways it is, but the core idea behind it is actually surprisingly simple. So, what exactly is an LLM? The best way to think about it is not as a thinking brain, but as a giant, incredibly powerful prediction machine. It's a special kind of AI that has been fed a mind-boggling amount of text data, all for one single purpose: to get ridiculously good at predicting the next word in any given sentence. Imagine this: you find a movie script, you see the human's line, but the AI's response is tone off. Your only job is to guess the very next word. You'd think about the context, the tone, what makes the most sense. You're playing a prediction game. And that's it. That's the fundamental secret. At its absolute core, an LLM is a stunningly sophisticated engine for predicting the next word. Every amazing answer, every piece of code, every poem, it all starts with this one simple goal: what word is most likely to come next? Now, the key word here is probable. The model doesn't just pick one single word it thinks is correct. It actually calculates the probability, the odds, for all possible words that could come next. And that's why if you ask the same question a few times, you might get slightly different answers. It's kind of rolling the dice among a set of really good options, which makes the conversation feel much more natural. So how does this one simple idea scale up into these massive systems? It really comes down to three key ingredients: a ton of data, a specific kind of architecture, and a whole lot of training. You can basically break down any LLM into these three parts: the data, the enormous library it learns from; the architecture, kind of like the brain that processes it all; the training, the teacher that guides that brain. And that brain, it's almost always based on something called the transformer, which completely changed the game back in 2017. Before this, models had to read text one word at a time, but the transformer could take in an entire sentence, even a whole paragraph, at once. It uses something called self-attention, which is like a spotlight that helps it focus on which words actually matter to each other. For example, in the sentence, "The cat, which was chased by the dog, ran up the tree." The attention mechanism helps the model understand that it's the cat that ran, not the dog. This gives it a deep, intuitive sense of context and meaning. Now let's talk about what makes them large. The scale here is almost impossible to imagine. Take GPT-3, it has 175 billion parameters. You can think of these parameters as tiny tunable dials inside the model's brain. Each one controls the strength of a connection between different words and ideas. As it trains, the model learns to adjust all 175 billion of them to capture the complex patterns of human language. And the data? If a person sat down and tried to read everything GPT-3 trained on, 24 hours a day, 7 days a week, it would take over 2,500 years. And if you try to do the math by hand, even at a billion calculations per second, it would take over 100 million years to finish the training. But this massive scale isn't just about having a bigger dictionary. At this level, something extraordinary happens. Emergent properties appear. Abilities like reasoning, summarizing, or logic, things no one explicitly programmed, start to show up naturally out of all that complexity. How does the training actually work? It all boils down to a super simple game of guess and check, just played trillions of times. During training, the model gets shown a piece of text like "the sky is," and its job is to guess the next word. At the start, all those billions of parameters are random, so its first guesses are total nonsense. It might predict bug or bird, then it compares that guess to the real answer, blue, and adjusts its parameters just a tiny bit to be less wrong next time. Repeat this over and over across trillions of examples, and that nonsense slowly transforms into coherence. This is how it learns patterns of grammar, facts, and even logic, not because anyone coded them in, but because it has statistically absorbed the relationships that define human language. Now, predicting the next word in a Wikipedia article is one thing, but how does that translate into answering your questions or following instructions? That takes a second step: fine-tuning. This is the two-step process for creating modern chatbots. First, there's pre-training, where the model learns everything about language by reading massive amounts of text. Then comes fine-tuning, where it learns its personality. Humans give feedback: thumbs up for helpful answers, thumbs down for bad ones. teaching it what's useful, clear, and safe. This tuning turns into a raw prediction engine into a conversational assistant. And the applications? They're exploding everywhere. Businesses are using large language models to power customer service chatbots. Individuals use them as writing and coding assistants. They're helping programmers debug faster, professionals summarize reports, and creators write scripts. You can even fine-tune a general model for a specific field, feed it legal documents, and you can create an expert assistant for lawyers, train it on medical journals, and you've got a tool that can help doctors research conditions. It's the same base model, just adapted to specialized knowledge. But as powerful as they are, we've got to stay realistic. These systems aren't perfect. LLMs can hallucinate, confidently generating things that sound true but aren't. And since they're trained on massive datasets pulled from the internet, they also pick up biases and misinformation. On top of that, the energy and cost of training them are enormous. To understand better, let's play a little game. I'm going to give you 3 facts. All you have to do is figure out what they have in common. Fact number 1, the distance from the Earth to our moon is 54 million kilometers. I mean, it sounds plausible, right? It's way up there. Fact number 2, and this one is about Dwayne Johnson. Before he started wrestling, he worked as a pilot. And for our third and final fact, the James Webb Telescope. It took the very first picture of an exoplanet, a planet outside our solar system. Sounds like a huge moment for science. They all sound perfectly plausible. An interesting fact, a bit of science, a cool historical note. The catch? Every one of them could be completely false. This phenomenon is called hallucination, because the model's only goal is to generate text that sounds probable. It sometimes just makes things up. It has no internal fact checker. Its mission isn't to be right, it's to sound right. The real distance to the moon is about 384,000 kilometers. 54 million would almost get you to Mars. And that airline pilot, nope, that's not him. As for the James Webb Telescope, the first exoplanet picture was actually taken way back in 2004 by a European Southern Observatory's very large telescope in Chile. And the Webb was just launched on December 2021. So, you got it yet? What's the connection between those 3 things? The answer is, they're all lies. Total fabrications. But they sound pretty convincing, don't they? Every single one of them was generated by an AI. Hallucinations show up in lots of ways. It might get basic facts wrong, ignore your question, contradict itself, or throw in irrelevant details. The key takeaway here is crucial. LLMs are not databases or encyclopedias. They are reasoning and generation engines. This isn't something that can be fixed just by feeding them more facts. It's a fundamental limit of a system built on probability, not truth. So always verify the information they give you. And here's the most important takeaway of all. Once you stop thinking of an LLM as this all-knowing genius and start seeing it for what it is, an incredibly powerful pattern matching engine, your whole relationship with it changes. You will stop being just a passive user who asks a question, and you will become an active operator who guides the tool to get exactly what you need. Look, at the end of the day, large language models are without a doubt one of the most powerful tools our species has ever created, but they're imperfect. And knowing their limits is every bit as important as knowing their strengths. But LLMs don't understand text directly. They process something much smaller and more fundamental. Let's talk about tokens. What's the actual commodity in the world of artificial intelligence? I mean, when we talk about ChatGPT, Gemini, or Claude, what are they really trading in? It's not oil, not electricity, not even data. It's something smaller, stranger, and far more valuable: the token. Well, we're pulling back the curtain on the hidden language that powers every AI system and the new form of currency that's driving this entire technological revolution. So let's dive right in. Think about it. You type something into a chatbot, maybe ask it for a story, and what you get back is amazing, coherent, creative, sometimes even funny, and feels almost human. But have you ever stopped to wonder what's actually going on inside that black box? How does a machine, just circuits and code, understand something as abstract as a word like brave? Well, the answer isn't what most people think. AI doesn't actually read English or Spanish or any human language. It has its own native tongue, a secret internal code completely hidden from us. And understanding that language is the key to get an idea how intelligence itself is built. When you get right down to it, under the hood, every single AI model breaks our world down into tiny, fundamental pieces of data. These pieces are called tokens. and they are the true building blocks of artificial intelligence. So, what's a token really? It sounds simple, but this one little concept is incredibly powerful, and it has some surprising quirks. The very first thing that has to happen inside an AI is a process called tokenization. You can think of it as a translation step. It takes our human data, whether that's text from a book, a photo you took, or even a clip of your voice, and chops it up into manageable pieces the AI can actually work with. A good way to picture it, think of tokens like atoms. Just as atoms are the basic building blocks of everything around us, tokens are the basic building blocks of how AI understands the world. Let's look at a real example. Say we give the AI the phrase, the word darkness. You and I see 3 words, but the AI might see it differently. It could break it down into subwords, dark and ness. Suddenly our short phrase is now 4 tokens, the, word, dark and ness. But hold on, chopping up words is only half the battle. At the end of the day, computers don't speak word or dark or ness. They speak numbers. So the next logical step is to turn all these little text tokens into something the machine can actually work with. Each one of those tokens gets assigned a unique ID number, kind of like an entry in a gigantic digital dictionary. Now here's where the magic starts. The AI later encounters another word, brightness. It splits that up too, bright and ness. And notice something cool. The token ness gets the exact same ID number as darkness, maybe number 655. By seeing that same shared token thousands and thousands of times, the AI begins to realize, ness describes a state or quality. In other words, it's learning patterns, learning meaning from numbers. To help visualize the scale of this, OpenAI gives a neat rule of thumb. For English, one token is roughly 3/4 of a word. So, if someone says a message is 100 tokens long, you can picture that as being about 75 words. Every chat, every image caption, every training sample, all of it gets broken down this way. But hold on, it's not quite as simple as it sounds. Let's say you use the word red. To us, red, a red and red at the start of a sentence are the same word. To AI, they are 3 completely different tokens, each with its own ID. Why? Because for a machine, context is everything. The lowercase r, the capital R, even the space before the word. Every tiny variation changes how the token is defined. So when people say AI doesn't understand words like we do, that's literally true. It understands patterns of tokens. Not words, not sentences, but sequences of numeric IDs that represent context. Okay, so now we know what tokens are. But how does an AI actually use them to do everything from writing essays to generating code? It all comes down to 2 phases: training, which is how the AI learns, and inference, which is how it uses that learning to actually answer your questions. During training, the model is fed a mind-boggling amount of data, billions, sometimes trillions of tokens, scraped from books, websites, research papers, and more. And the task it performs is beautifully simple. The AI sees a string of tokens, something like the cat sat on the and its only job is to predict the next token. If it guesses mat and the training data agrees, great. But if it guesses floor, that's wrong. So it learns from the mistake, tweaks its internal wiring just a tiny bit, and tries again. Do that billions of times, and it becomes frighteningly good at guessing the next token. That's all learning really is, predicting what comes next in a sequence. Now once the AI is trained, you and I interact with it through the second phase, inference, the part where it applies everything it learned to our prompts in real time. And this is where another key concept appears, the context window. The context window is the total number of tokens the AI can keep in its mind at one time. Think of it like short-term memory. When you start chatting, your question and the AI's response both get turned into tokens and stored in that window. As long as the entire conversation fits inside it, the AI remembers everything perfectly. But what happens when we keep talking? Eventually, you're going to hit the token limit of that window. As soon as you go past that limit, something strange happens. To make space for new tokens, the oldest ones get pushed out, and the AI literally forgets them. That's why, after long conversations, chatbots sometimes lose track of context or repeat themselves. It isn't that they're confused, they just ran out of memory space. The good news? The context window is getting bigger fast. Early models could handle maybe 2,000 tokens, a few pages of text. Modern ones process over 1 million tokens, enough to read and analyze an entire novel at once. But bigger windows come with trade-offs. double the size, and the compute cost doesn't just double, it quadruples. And strangely, some models get worse at remembering information buried deep in the middle of very long contexts. So, as always, progress brings new challenges. Here's where everything ties together. Tokens aren't just a language for AI, they've become a currency. Every single token an AI reads or generates consumes computing power, energy, GPUs, time, and those resources cost real money. That simple fact has created the entire business model of modern AI. I absolutely love this quote from NVIDIA's CEO Jensen Huang, which frames it perfectly. AI heralds a new era of innovation, and now we have ability to manufacture intelligence. Think of these giant data centers as AI factories, and what product are they making? They're manufacturing intelligence. The raw material is data, and the unit of production that you measure, that you buy, that you sell is the token. Companies like OpenAI, Anthropic, and Google charge for usage by counting tokens. You pay for input tokens, what you send, and output tokens, what the AI sends back. Summarizing a long document means lots of cheap input tokens, but only a few expensive outputs. Writing a poem flips that: few inputs, many outputs. So when you're chatting with an AI, you're effectively making a microtransaction of intelligence. You spend tokens to receive tokens. And those massive GPU clusters you hear about, they're the factories producing intelligence. Their raw material is data, the finished product is meaning, and the unit of production, the thing that gets counted, priced, and optimized, is the token. Even metrics inside AI development revolve around tokens. Time to first token measures how fast an AI starts responding. Throughput tracks how many millions of tokens per minute it can generate. Everything in this new industry, cost, speed, memory, even intelligence itself, circles back to one small unit. Of course, there's always a flip side. As context windows expand, so do expenses. Compute costs rise quadratically, and keeping trillions of tokens in motion demands staggering energy. There's also the question of reliability. Bigger memory doesn't always mean smarter results. Models can hallucinate, forget middle details, or even be manipulated through hidden prompts buried deep in the text. So efficiency has become the holy grail. Hardware leaders like NVIDIA have slashed token processing costs by 20 times with new GPUs and optimized software stacks. Because in the world of AI, making tokens cheaper and faster is everything. Okay, let's make this practical. Why should you, an everyday user, even care about what a token is? It really comes down to three things: cost, speed, and coherence. Lengthy prompt and response directly impact price. So more words in or out equals more tokens equals higher cost. Token processing determines how fast you get a response. So faster models equal quicker time to first token. And a larger context window equals better memory and flow in long conversations with more consistent answers. The next time you type a prompt, remember, you're not just asking a question, you're conducting a trade in the new economy of intelligence. Input tokens go in, output tokens come out. That's the invisible currency behind every conversation you have with AI. We started this journey by calling tokens the building blocks of language, and now they're the units of thought, memory, and even value. They're not just fragments of data anymore. They've become the way intelligence itself is measured, manufactured, and sold. It raises a fascinating question for our time. If intelligence can be priced per token, what's the cost of a thought? What's the true value of an idea in a world where machines can generate billions of them every minute? We are watching in real time the birth of a new economic unit, the token, and with it, perhaps the first true currency of artificial intelligence. Now that we know how AI sees text, let's uncover the architecture that actually makes AI powerful, the transformer. Let's be honest, you've probably talked to it. Maybe you've asked it to write a silly poem or help you out with your homework. But have you ever actually stopped and wondered what's going on inside ChatGPT's brain when it spits out those crazy human-like answers? Well, today we're going to pull back the curtain. But how does it do that? How does an AI write a story or whip up an image or just talk like a person? You type something in and then you see it, right? It responds word by word, almost like it's thinking. But what is really happening inside that black box? How does a machine create something that feels so human? And how does an AI seem to just understand you? You know, it really does feel like magic sometimes, doesn't it? But it's not. The entire AI revolution that we're living through right now, it all boils down to one single, incredibly powerful idea that first showed up back in 2017. A team of researchers came up with a totally new way of looking at the problem. It all revolved around one single powerful concept. It all started with this paper with maybe the best title in computer science history, "Attention is All You Need," which introduced the term transformers. Later in 2018, Google released BERT, which revolutionized search with bidirectional context, and 2020 OpenAI came up with GPT-3, a powerful generative model that revolutionized the world. And the name pretty much gives the game away. GPT, it stands for Generative Pre-trained Transformer. Okay, so generative, that's easy. It generates stuff, creates new things such as images, videos, or content. Pre-trained also makes sense. It's been trained on a truly insane amount of data. But that last word, transformer, that's the key. That's the secret sauce. So, what exactly is this thing called a transformer? It's not just some other fancy neural network. This was a completely new architecture that changed the game for AI. Before transformers, older models like RNNs could only read text one word at a time, left to right, like us. They struggled to keep track of context, especially in long sentences. But the transformer cracked that problem wide open with a revolutionary idea called self-attention. This mechanism allows the AI to look at an entire sentence at once and figure out for itself which words are the most important and related for understanding other words in that sentence. It literally learns where it should focus its attention. Let's make this real. Look at this sentence. Now, the word sentence could mean a couple of different things, right? Is it like a string of words with a period at the end, or is it legal punishment? How on earth does an AI know the difference? Well, this is where that attention mechanism comes in. The model learns that to figure out the meaning of sentence, it needs to pay extra attention to the words judge and issued. Those are the magic context clues. It figures out judges issue legal sentences, not a lawyer. So here's the key takeaway. Attention lets the model dynamically decide how important other words are. It's not just reading from left to right anymore, it's building this incredible complex web of relationships between all the words to figure out what they really mean in that specific context. That single innovation, attention, is what allows AI to understand relationships and meaning, not just text. The transformer architecture has two main parts, the encoder and the decoder. The encoder reads and understands the input, for example, your prompt. The decoder then uses that understanding to generate a meaningful response. In ChatGPT and similar models, both sides are deeply intertwined. The encoder absorbs meaning, and the decoder predicts the next word. That's how it learns to turn understanding into creation. Originally, the transformer setup was built for translation, turning one language into another. But it turns out that this same structure works astonishingly well for everything: writing, coding, AI image generation, summarizing books, generating video, speech recognition, and even predicting things like stock market trends. That same core idea of attention works for all of it. It's just incredible. But wait a second, how does that even work? An image isn't a sentence, right? So how can a transformer process it? Well, the solution is just brilliant. A vision transformer first chops up an image into a bunch of little patches like a grid. Then it treats each one of those little patches as if it were a word. It turns it into a vector. After that, it just feeds this new sentence of image patches into the same self-attention mechanism we've been talking about. This lets the model learn how all the different parts of the image relate to each other. You know, how a cat's ear connects to its head and its tail to understand the whole picture. So how does the magic trick, predicting the next word, works? For all its incredible power, the fundamental job of a model like ChatGPT is shockingly simple. And this might sound crazy. It's basically a supercharged version of the autocomplete on your phone. Seriously, it's all about one thing: predicting the next word. Here's how it works. You give it a prompt, your starting text. The model looks at that and predicts the most likely next word. It adds that word, then repeat it again. That word-by-word generation you see on your screen, that's literally the loop in action. Early models that tried this produced gibberish. But when researchers scaled up the data and parameters, suddenly coherence appeared. The same loop started producing stories, poetry, reasoning, even creativity. That's the power of scale. So if the core trick is just predicting the next word, the real question is how? How does it make that prediction so incredibly well? Let's pop the hood and follow the data on its journey from the moment you hit enter to the model's final response. Let's follow the data from the moment you hit enter. First, tokenization. Your text is broken into small chunks called tokens. Second, embedding. Each token is converted into a long list of numbers representing meaning. Now here's where positional encoding comes in. Because transformers look at all words at once, they don't naturally know the order of words. So positional encoding gives each word a kind of timestamp. It tells the AI that man bites dog is different from dog bites man. Without sequence, the whole structure of the sentence falls apart. All those sequences of vectors then passes through an operation that's known as attention block, and this allows the vectors to talk to each other and pass information back and forth to update their values. For example, the meaning of the word model in the phrase a machine learning model is different from its meaning in the phrase a fashion model. The attention block is what's responsible for figuring out which words in context are relevant to updating the meanings of which other words and how exactly those meanings should be updated. And again, whenever we use the word meaning, this is somehow entirely encoded in the entries of those vectors. After that, these vectors pass through a different kind of operation, and depending on the source that you're reading, this will be referred to as a multi-layer perceptron or maybe a feed-forward layer. And here the vectors don't talk to each other, they all go through the same operation in parallel. Each layer builds a deeper understanding of meaning and relationships, like layers of reasoning stacking up. Finally, the model uses all that to predict the next token. And the scale of this system is mind-blowing. GPT-3, for example, has about 175 billion parameters, little tuning knobs that collectively define what the model knows and how it responds. One of the most elegant ideas in all of AI is word embedding. Imagine a gigantic multidimensional library where every word sits on a shelf next to other words that share meaning. That's what embedding is. It's math for meaning. If you take the vector for king, subtract man, and then add woman, you end up astonishingly close to queen. The model has learned concepts, relationships, analogies, even emotions just by reading text. It's not memorizing words. It's learning the geometry of ideas. After processing all those numbers, the model generates a score for every word it knows. A mathematical function called softmax converts those scores into neat probabilities that all add up to 100%. Then it picks one and the next word. But here's the fun part. It doesn't always pick the highest one. There's a creativity dial called temperature. Low temperature means predictable, factual, safe answers. Balanced temperature means more creative, surprising, sometimes weird responses. Too high, it goes off the rails and at times just spills out nonsense. That's literally how you control whether your AI sounds like a scientist or a poet or who is totally nuts. Even though we think of them as text tools, transformers are everywhere now. They power DALL-E and Midjourney for image generation, Whisper for speech recognition, Gemini and Claude for reasoning and writing, and even AlphaFold, which revolutionized biology by predicting protein structures. This single architecture, transformer, has become the backbone of the modern AI era. What's the real magic here? It's not magic at all. What feels like creativity or intelligence is really the emergent result of simple mathematical patterns, scaled to unimaginable size. It's all about understanding the relationships between words, turning them into numbers and then predicting what comes next. But that simplicity is its beauty, because from that single humble rule, predict words, emerges everything we now call intelligence. And that leaves us with a final question. If a machine can write poetry, explain physics, and hold a conversation, all by predicting the next word, what does that say about us? What will we ask it to understand next? With transformers, AI can finally understand text like humans do. So let's look at the field that makes computers understand language. Let's talk about something that's pretty much everywhere, but you might not even notice it. I'm talking about natural language processing, or NLP. It's this silent revolution that's teaching computers to finally speak our language. Think about this. You ask your phone for directions. You tell it to set a timer. You dictate a text message half asleep, and somehow it just understands. How does a piece of metal and silicon make sense of the way humans talk, full of slang, pauses, and incomplete sentences? Well, spoiler alert, it's not actually magic. It's NLP. And it's the engine behind pretty much everything you see here. We're talking Siri and Alexa, your Google searches, those customer service chatbots, even the voice on your GPS. It is literally woven into the fabric of our digital lives. So, What exactly is NLP? Think of NLP as the ultimate translator, the bridge between our messy human world of words and the superlogical computer world of ones and zeros. So, here's the official breakdown. Natural language processing is a part of AI, right? And its whole mission and one big goal is to give computers the power to read, understand, interpret, and even generate human language. And that goes for both text and speech. And how does it pull this off? Well, it's not just one thing. It's this awesome mix of three powerful disciplines. You've got computational linguistics. That's kind of like the old school grammar textbook with all the syntax and hard-coded rules, but then it adds in machine learning and deep learning, and that's the secret sauce. It lets computers go way beyond just following rules and lets them actually learn the patterns in the context from just tons and tons of data. That blend, old school grammar meeting modern AI, is what allows machines to move from simply recognizing words to actually understanding meaning. But this technology didn't just pop up out of nowhere. It actually has a fascinating history growing from this niche academic idea into a force that is completely reshaping our world. So let's take a quick look at that journey. The seeds of NLP go way back, the 1950s, with these tiny experiments like translating just 60 sentences from Russian to English. Then by the 90s, things got more practical. It was the tech behind the spam filters that cleaned up our inboxes. But the real earthquake hit in the 2010s with deep learning. That's what gave computers the power to analyze massive chunks of text. And all that leads us to today, where generative AI has completely flipped the script, where NLP has evolved from merely understanding language to actually creating it. Okay, so that's the history lesson, but where does this technology actually show up in our daily lives? I bet you're interacting with it way more often than you realize. Start with a really important one that happens completely behind the scenes. In fields like law, insurance, or healthcare, you've got mountains of documents just filled with private information. I mean, trying to go through and out all that sensitive data by hand, it'd be totally impossible. And this is where NLP becomes a superhero. It can scan millions of pages and automatically find and redact all that sensitive stuff. We're talking about policy numbers, social security numbers, private medical details. A great real-world example is a company called Chisel AI. For them, NLP isn't just a cool tool, it's a critical layer of security that protects people's privacy. Now, here's one you have absolutely run into probably even today: customer service. NLP is the brainpower behind all those chatbots and voice assistants we talk to all the time. It's what lets those bots understand what you're really asking, making them feel a little less robotic. Companies like T-Mobile use it to scan text messages for certain keywords so they can offer you personalized deals. Even universities like Oklahoma State are using chatbots to answer student questions anytime, day or night. It's all about making things faster and hopefully better. And here's another really powerful way businesses are using it: to understand how their customers are really feeling. This whole idea is called sentiment analysis. Just imagine being able to scan thousands of product reviews, social media comments, and call transcripts to get a real-time pulse on your customers. Like, are they happy? Are they frustrated? NLP tools do exactly that. You've got platforms like Success KPI that use this to turn raw call data into a crystal clear picture of customer feelings that help businesses understand their audience in real time. So, in short, NLP gives machines the ability to not just listen, but to feel the pulse of human conversation. Okay, so we've seen all the cool things NLP can do, but how in the world does a machine even begin to untangle something as messy and complex as human language? Let's lift the hood and see how it all functions. Language, as we know, is chaotic, full of ambiguity and context. So NLP systems start by breaking it into structured building blocks, kind of like disassembling a sentence to study its parts. This happens through two main types of analysis. On one hand, you've got syntactical analysis. This is pure grammar, the rules. It's the part that knows if a word is a noun or a verb, and if the sentence structure is correct and makes grammatical sense. But on the other hand, we have semantical analysis. It looks at meaning. Understanding that bank can mean a river bank, or a financial institution depending on context. Together, syntax and semantics help machines grasp what you said and what you meant. Okay, that's the what. But now the big question. So what? Why does any of this actually matter in our daily lives? Well, the real-world value here is huge. Let's get into the benefits. For starters, it automates all those boring, repetitive tasks. It helps us find incredible insights from just oceans of text data. Think of product reviews or social media posts. It totally transforms how we search. Modern NLP doesn't just interpret, it can write. Articles, emails, captions, and reports can now be generated in seconds, often indistinguishable from human writing. And maybe the craziest part, it can even generate brand new human-like sounding content, all on its own. Let's just take automation for a second. Imagine you're running a business. Instead of having a person answer the exact same question, like, "What time do you close?" over and over and over again, a chatbot powered by NLP can do it instantly, 24/7. And just like that, you freed up a person to solve the difficult problems that need a real human brain. And search, that's a big one. Remember old school search? It was just keyword matching. You typed bear, you got the fluffy animal, that's it. But an NLP-powered search, it gets the context. It can figure out if you mean the animal or the slang for a big, hairy person. See the difference? It's about what you mean, not just the word you type. In short, NLP makes digital systems more human-aware, understanding what we mean, not just what we type. So how do we get from these clunky basic systems to the incredibly smart ones we have today? It's been a really fascinating journey, a real evolution of thinking. In the beginning, it was all rules-based, just simple if-then statements. But that was super rigid. It would break the second it saw a typo or some new slang. So we evolved to statistical NLP. This was smarter. It used machine learning to figure out the most likely meaning of a sentence. A big step up. But the real revolution, the thing we're living in now, is deep learning NLP. This uses these massive brain-like neural networks and just incredible amounts of data to get a way more nuanced understanding of language. So today the whole process works kind of like an assembly line. Step 1 is pre-processing. You got to clean up all the messy raw text. Think of it like tidying up a super messy room before you can find anything. Next, feature extraction. This is where you turn all those nice, clean words into numbers a computer can actually work with. Then, and only then, can the real analysis start, where the machine starts identifying patterns. And finally, you have model training, which is basically where the machine practices until it gets really good at finding those patterns by itself. And that analysis step we just talked about, that's where some seriously cool stuff happens. It's not just one thing. You've got part of speech tagging. That figures out what's a noun, what's a verb, and so on. Then it moves on to bigger things like named entity recognition. Recognizing that Sarah is a person and Paris is a city. Each step adds another layer of understanding. This right here illustrates the single biggest challenge in all of NLP: ambiguity. The word bat could be a flying animal, or it could be what you use in baseball. We get the difference from context, right? Well, teaching a machine to do that same thing is a huge task, and it's called word sense disambiguation. And this sentence is a perfect example of two more key tasks. So through named entity recognition, the computer identifies Jane as a person and France as a place. Simple enough. But then using something called co-reference resolution, it figures out that the word she refers back to Jane. That might seem obvious to us, but for a machine, it's absolutely crucial for following the plot of a story or a conversation. If you zoom out from all those little tasks, the entire process pretty much follows this three-step recipe. First step is pre-processing, where all the messy raw text gets cleaned up and simplified. Next comes the training, where the computer model chews on massive amounts of that cleaned up data to get better and more accurate. And finally, you have deployment, where the trained model is put out into the real world to start working on new live information. Now, it's easy to think this technology is perfect, but it's not even close. Human language is just so messy and creative, and it's always changing, and that creates some major headaches for computers. And here are some of the biggest hurdles. First up, biased data. This is a huge one. If you train AI on biased information, guess what? You're going to get a biased AI. It's garbage in, garbage out. Then there's just us. The way we talk, slang, dialects, sarcasm. Computers are terrible at sarcasm. How do you program a machine to understand that when someone says, "Oh, that's just great"? They might actually mean it's terrible, and we're always inventing new words. It's that subtle human context that's still the final frontier for these systems. And that brings us right up to the present moment, because the entire field is going through a massive shift. We are moving way beyond just processing language and into a world where we're actively generating it. This is the huge breakthrough that's happening all around us. Thanks to generative AI, those core ideas of NLP are now being used to create incredibly human-like text. Everything from a single sentence to an entire article. It's a gigantic leap from just analyzing language to actually creating it from scratch. So, what does this new superpower actually let us do? Well, think about getting an instant summary of an hour-long meeting you missed, or drafting a professional-sounding email from just a few bullet points, or having a conversation with someone in another language translated in real time. This isn't science fiction anymore. These are the tools that are changing how we work right now. So, if there's one big idea to take away from all of this, let it be this one. Mastering language is no longer just a human skill for companies, for individuals, for everyone. NLP is turning communication itself into a powerful tool and a real competitive advantage. And that leaves us with one last pretty big question to think about. Now that our machines can speak our language, it's not just about us talking to them anymore. It's about how this new two-way conversation is ultimately going to change us. Something to chew on. Language is one part of intelligence. Another huge part is vision, how AI sees the world. Let's explore computer vision. Have you ever stopped to think about how your phone unlocks just by looking at you? Or how can some cars just drive themselves? Well, the magic behind all of that is a field of AI called computer vision. And today we're going to dive in and break down exactly how we're teaching machines to actually see and understand our world. Okay, so to really wrap our heads around what computer vision is, let's start with a problem that seems pretty simple for us humans, but is, incredibly complex for a machine. Just think about it for a second. A self-driving car is dealing with this constant chaotic flood of visual information, and it has to process it all in real time. It needs to spot the lane markers, read traffic signs, and tell the difference between a person, a bike, and maybe a fire hydrant. So, how in the world does a machine do all of that? Well, the answer is computer vision. So what is it really? At its core, computer vision is all about giving computers a high-level understanding of what's in an image or a video. We're going way beyond just capturing pixels here. We are teaching machines to pull out meaningful information from that visual data pretty much the same way our own brains do. You see, at the end of the day, the goal here is to copy one of our most powerful senses, our sight, and also the incredible brain power that goes along with it. When we look at the world, we don't just see colors and shapes, right? We understand the context, we make judgments, we make decisions. That is the amazing ability we're trying to give to machines. So how does this learning process actually work? To really understand how this works, let's switch to a powerful example from medicine where computer vision is already saving lives by spotting pneumonia on chest x-rays. The whole thing really boils down to this 4-stage pipeline. First, you've got to gather the raw materials, the data, then you prepare it and clean it up. After that, the real fun begins. You train the AI model, and finally you deploy it out into the real world. Let's start right at the beginning with the absolute foundation of it all, the data. Think about it. Any intelligence, whether it's human or artificial, has to learn from something. For an AI, its entire education comes from data. You can think of this data as its textbook. And just like with any student, the quality of that textbook is going to determine how much it can actually learn. So, for a pneumonia detector, the textbook is a massive collection of hospital chest x-rays. But here's the catch. The images by themselves are totally useless. The real secret sauce is the labeling. This is where human experts, in this case radiologists, go through every single scan and tag it normal or pneumonia. Those little labels are what turn a bunch of meaningless pixels into powerful lessons for AI. So just to be super clear, labeled data is simply information a human has given context to. It's basically like creating flashcards for AI. You show it an image of lungs and say, this is normal. You show it another with cloudy spots and say, this is pneumonia. Without labels, they're just pictures with them. They become the bedrock of the AI's knowledge. But here's the thing about raw data from the real world. It's almost always messy, so just like you'd proofread a textbook before handing it to a student, the data needs to be cleaned and standardized. We're talking about getting rid of blurry images, making sure all the scans are aligned the same way, normalizing brightness. This pre-processing is absolutely vital because you want the AI to focus on the real patterns of the disease, not get confused by random noise. Alright, so we've got our clean, perfectly labeled textbook. Now it's time for the AI to actually go to school. This is the training phase, and this is where the real learning finally begins. But you wouldn't give a student the answer key to the final exam on the first day, right? Of course not. So before training even starts, all that data gets split into 3 separate piles. The biggest chunk, the training set, is for the day-to-day learning. A smaller validation set is used for little pop quizzes to check its progress, and the last part, the test set, gets locked away in a vault, completely untouched until the final exam. And this separation is non-negotiable. It's incredibly important. The goal isn't to create an AI that just memorizes the training images like a parrot. We need it to genuinely understand the underlying patterns of pneumonia. By keeping that test data completely separate, we can be sure we are evaluating its real-world knowledge, not just its ability to cram for a test. Now here's something most people never see. During training, the model keeps checking its performance on that validation set. If it starts getting better on the training data but worse on validation data, that's a warning sign called overfitting. It means the AI is memorizing instead of truly learning. Those validation checks help us stop training at the perfect moment, right before things go wrong. And here's another behind-the-scenes layer: hyperparameter tuning. This is where we fine-tune the rules of how the AI learns. Things like how fast it should learn, how many images it sees at once, how deep its neural network should be. These tweaks might sound small, but they massively affect how well the model performs. So what's the actual brain doing all this learning? Well, it's a special kind of AI model called a convolutional neural network, or CNN for short. The easiest way to think about it is as a system inspired by how the human visual cortex works. It learns to recognize simple things first, textures, and then builds that up to understand far more complex patterns, including the subtle signs of disease. During training, CNN looks at thousands and thousands of these labeled X-rays over and over again. For each one, it makes a guess: pneumonia or normal. Then it checks its answer against the real label and, if it's wrong, makes a tiny adjustment to its internal wiring. Repeat this millions of times, and those tiny adjustments add up until it becomes incredibly good at spotting the patterns it's looking for. After all that training and studying, it's time to see what our AI has really learned. This is the final exam, the moment of truth where it must prove it can solve problems which it has never encountered before. This is when we unlock that vault and bring out the test set. Its performance on these fresh, unseen images is the single truest measure of its ability. This isn't a practice run, this is our best prediction of how it will perform in a real hospital. And we don't just give it a simple pass or fail, we measure its performance with very specific metrics. Accuracy, how often is it right? I mean overall accuracy. Precision, when it says pneumonia, is it correct? Recall, of all real pneumonia cases, how many did it catch? Together, these give us a detailed report card on the AI. Now, assuming the AI passes its exams with flying colors, it's ready to graduate from the research lab and begin its career in the clinic. But before that, there's one final behind-the-scenes step: model exporting and optimization. We need to convert the heavy model into a lightweight, fast format, like ONNX or TensorRT, so it can run instantly on real hospital systems. Think of it like taking a huge textbook and turning it into a pocket guide the doctor can use in seconds. Now finally, the AI, which is optimized tools, is ready for deployment. Now that we have a sense of how it learns, let's check out what computer vision can actually do. And it's not just one single trick. It's really a whole toolbox filled with amazing capabilities. Okay, let's start with an important distinction: object detection versus image segmentation. So, with object detection, the AI draws a simple box around something and says, hey, there's a bicycle in this box. But image segmentation, that goes a huge step further. It outlines the exact pixel-perfect shape of the object. And that level of detail is absolutely critical for things like, say, defining the precise boundary of a tumor in a medical scan, or for a self-driving car to know the exact shape of a pedestrian it needs to avoid. Next up is a capability that I bet a lot of us use without even realizing it: optical character recognition, or OCR. This is basically how we teach computers to read text right out of images, and totally changing how banking and healthcare are handling paperwork. And this technology is just everywhere. OCR is what lets you point your phone's camera at a menu in another language and get an instant translation. It's also the powerhouse behind digitizing mountains of old paper records, completely automating data entry, and saving just countless hours of boring manual work. Of course, we have to talk about facial recognition. This is probably the most well-known and sometimes controversial application of computer vision. The system is trained to identify or verify a person based on their unique facial features. And you really do see it everywhere. It's what unlocks your smartphone 100 times a day. It's used for secure biometric login on your banking apps. And it's what's helping to speed you through some of those security lines at the airport. It all works by mapping the unique geometry of a face. Things like the distance between your eyes or the shape of your chin. And hey, if these videos help you understand AI better, make sure to subscribe so you don't miss any upcoming deep dives. So, when you start to put all these different capabilities together, you begin to see how computer vision isn't just a cool tech demo. It's fundamentally changing entire industries. I mean, in healthcare, the impact is huge. It goes way beyond just flagging pneumonia. We're talking about systems that can precisely outline tumors for radiation therapy and even give surgeons real-time guidance and data during incredibly complex operations. In transportation, it's obviously the core technology that makes self-driving cars possible, but it's also used to manage traffic flow in smart cities, optimizing stoplights to reduce congestion. And get this, NASA has even used it to help spacecraft land safely on other planets by identifying and avoiding dangerous rocks and craters. How cool is that? And then you have retail and manufacturing, where it's a total game changer. It's the engine behind those cashierless stores where you can just walk out. It powers those virtual try-on apps that let you see how clothes look on you. And on the factory floor, it's tirelessly inspecting products on an assembly line, spotting tiny defects with superhuman speed and accuracy. In agriculture, drones fly over fields, monitoring crop health from the sky. And of course, it brings us full circle back to healthcare, where these systems are assisting doctors with the very same complex medical scans we started with. All of this stuff feels incredibly futuristic, almost like something out of a sci-fi movie. But the truth is, this overnight revolution has actually been decades in the making. So let's take a quick trip back in time and see how we got here. The story really starts way back in the 1960s, with scientists studying how a cat's brain responds to simple lines and edges. Super foundational work. Then fast forward to 1982, when a guy named David Marr laid out a groundbreaking theory of how vision works. But the huge leaps came much later. In 2009, we got the ImageNet dataset arrived, which is a total game changer, giving researchers millions of labeled images to train their systems on. And then came 2012. A neural network called AlexNet used that data and shocked the world. It didn't just win a competition, it proved deep learning could slash error rates and achieve accuracy levels nobody thought were possible. That breakthrough kicked off the entire AI boom we're living in today. And that brings us right back to now. This technology is already amazing, but you know what? It's still evolving so rapidly. So the big question is, where is this all headed? Well, there are three huge trends shaping the future. First, there's Edge AI. This is all about doing the processing right on the device itself, like in a self-driving car, instead of sending data to the cloud. It's way faster and much more private. Second is multimodal AI, which is about combining vision with other senses like language and audio to build a much richer, more context-aware understanding of the world. And finally, there's a massive push for ethical and explainable AI, developing systems where we can actually understand why they made a certain decision, making them more transparent and less biased. And that brings us to our final thought for today. The power of computer vision is just undeniable. We are giving machines a sense that until now it was purely biological, and the companies with this ability are going to lead industries. But with this incredible new power comes profound responsibility. So the question we're all left with isn't just about what machines can see anymore. It's about what we as a society decide they should be allowed to see. The last core pillar of modern AI is how machines learn from trial and error. This is where reinforcement learning comes in. Have you ever watched a robot in a video game and wondered how it got so smart? Or thought about how a self-driving car learns to navigate a tricky intersection? It's not always about a programmer writing millions of lines of code for every single possibility. A lot of the time it's about learning from trial and error. Kind of like we do? Well, today we're going to dive into that amazing world of reinforcement learning. And the big question, how can you get a machine to explore a brand new world, figure out what works and what doesn't, and get better over time all by itself? It all comes down to this really powerful feedback loop of actions and consequences. To really wrap our heads around this, let's follow a little hero on a quest. Our hero is a simple agent and its big challenge is to solve a maze. Here's the catch. It has no map, no instructions. All it can do is try stuff and learn from what happens. But before our hero can start his journey, we've got to meet the key players. we need to understand the basic rules of the game it's playing. First up, we have the agent. This is our learner, the one calling the shots. In our main story, it's this little robot. But in the real world, an agent could be anything really. A self-driving car, a dog, an algorithm playing chess, you name it. The agent doesn't just exist in a vacuum, it operates inside an environment. This is its world, its playground, the whole shebang. For our little robot, the environment is the maze itself. All the open paths, the dead ends, and those pesky walls. At any given moment, the agent finds itself in a specific state. Just think of it like a snapshot of its current situation. For our maze runner, the state is super simple. It's just its exact location, it coordinates inside the maze. And from any state, from any spot in that maze, the agent can take an action. These are the choices it has. For our hero, it's straightforward. It can move up, down, left, or right. That's it. And here is the absolute key to everything: the reward. After every single action, the environment gives the agent some feedback. Maybe it's a huge positive reward for finally reaching the goal, or it could be a negative penalty for bumping into a wall. This feedback system is literally how it learns what to do and what to avoid. Another example could be training a dog. You don't hand your puppy a textbook on the philosophy of sitting, right? When the dog happens to do the right thing, it sits. It gets a reward, a treat. And over time, it builds this connection. It understands that when it does this action, it gets that treat. That simple feedback loop, that idea of learning from rewards, that is the absolute heart of reinforcement learning. How does learning actually happen? Well, it happens through this constant trial and error loop. You can think of it like the agent's own personal training montage where it's on a quest for knowledge. This is the engine that drives it. First, the agent looks around. It observes its current state. Then it picks an action based on its current strategy, which we call a policy. It acts and the environment gives it a reward or a penalty. Based on that feedback, the agent updates its strategy and then it repeats it all over again and again and again. Thousands, maybe millions of times. That's how it builds mastery. Let's see this in action. In the very beginning, our agent is totally clueless. During its first try, its first episode, its path is just chaos. It's moving randomly, bumping into walls with absolutely no idea what it's doing. It's pure exploration. Okay, let's go fast forward to episode 100. Now things are looking a little different. The agent has learned a few things. It's starting to figure out which moves are bad, and it's kind of heading in the right direction, but it's still making mistakes, still taking wrong turns. It's better for sure, but it's not perfect. And after 5,000 episodes, bam, the agent has found the optimal path. It has learned to perfectly balance exploring new routes with exploiting the ones it knows work best. It didn't just find a path, it found the best path. It has officially solved the maze. And hey, if these videos help you understand AI better, make sure to subscribe so you don't miss any upcoming deep dives. Solving a maze is a pretty cool thing. But obviously this technology goes way beyond that. But where does technology actually pop up in our lives? Let's take a look at some of the real-world places where reinforcement learning is having a massive impact. Robotics is one of the biggest. I mean, instead of trying to program a robot arm for every single possible movement, you can create a digital version of it in a simulation. There it can try and fail thousands of times to learn how to pick up an object or how to walk without breaking anything expensive. Once it figures it out in the virtual world, that knowledge gets beamed over to the real-world robot. Self-driving cars are another huge one. The real world is just impossibly complex. So by combining reinforcement learning with deep learning, a technique called deep reinforcement learning, the car's AI can learn from millions of simulated miles. It processes tons of data from its sensors and learns how to make these incredibly complex split-second decisions, all guided by rewards for driving safely and efficiently. And of course, gaming. You've definitely heard about AI mastering insanely complex games like chess or Go. That's reinforcement learning. The agent literally learns by playing against itself for thousands of years worth of games. But here's the cool part. That exact same technology is used to create hyper-personalized experiences for you. Let's say while shopping in Amazon or watching movies on Netflix, this same technology recommends what next to watch or to buy based on the reward of you clicking on it. It's also helping machines learn super precise movements for building things in factories, and even being used to optimize huge industrial processes and create personalized learning programs that adapt to you. That feedback an agent gets generally comes in two main flavors. You've got positive reinforcement, which is like giving it a treat for doing a good job. This really allows the agent to maximize its performance. Then there's negative reinforcement, which is more about avoiding something bad like an electric shock or a penalty. This makes sure the agent learns to meet at least a minimum standard. So where does all this learning data come from? Well, with online RL, the agent learns live, interacting in real time. Think of a video game AI that's adapting to your every move. But with offline RL, it learns from a big static dataset that's already been collected. This is crucial for situations where mistakes are a big deal. I mean, you wouldn't want medical AI learning by trial and error on real patients, right? Offline is way safer when the stakes are high. Now, you might be thinking, is this the only way machines learn? And the answer is no, not at all. It's really important to know that reinforcement learning is just one of 3 major ways we teach AI. So let's quickly put it in context. This table really breaks it down. With supervised learning, you're basically giving the AI an answer key, a massive dataset where all the correct answers are already labeled. Think, this is a cat or this is a dog. With unsupervised learning, you give it the data, but no answers, and you just ask it to find interesting patterns on its own. Reinforcement learning, it's a totally different beast. There is no dataset to start with. The agent creates its own data as it goes, learning purely from the consequences of its actions in the world. Now, as incredible as reinforcement learning is, it's definitely not a magic wand for every problem. So it's really important we take a balanced look here at both its amazing power and its potential pitfalls. On the plus side, the advantages are just huge. Reinforcement learning can solve ridiculously complex problems that other methods can't touch. It adapts on the fly to new situations, and you don't need to hand feed it perfectly labeled data. And maybe the coolest part, it can discover totally new creative strategies that a human might never even think of. It's a real engine for innovation. But there are some serious hurdles. Reinforcement learning can be a beast, requiring massive amounts of data and computer power. And designing that reward system is tricky. If you get it wrong, the agent might learn to do something completely bizarre. There's this famous story of an AI that was supposed to win a boat race, but it figured out it could get more points just by driving in circles, hitting bonus targets, instead of ever finishing the race. And of course, when you're talking about real-world robots, you must make sure they can learn safely without, breaking things during that trial and error phase. Plus, these systems can sometimes be a black box, where they make brilliant decisions, but we have no idea why. It's a powerful tool, no doubt, but one you must use carefully. Which brings us to a final thought. Our little agent learned to solve a maze. Bigger, more complex agents are mastering games and running factories. So the real challenge isn't just building a smarter AI, it's about defining the right goals in the first place. As we give machines this credible power to learn for themselves, we must be extremely careful about what we are asking them to achieve. The future of this tech really depends on the wisdom of the rewards we design. Congratulations! You've just learned the entire foundation of modern AI, from neural networks to transformers, NLP, vision systems, and reinforcement learning. Phase 2 starts next, where we go deeper into the advanced world of AI tools, models, and real-world applications. Subscribe to UTC AI Studio because your AI journey has only just begun. Thanks for watching UTC AI Studio, AI-powered, creativity-fueled. I'll see you in the next video. Till then, as always, keep learning, keep building, and keep creating with AI.